Hello and welcome to another video. So today we're going to be doing problem number 2763, sum of imbalanced numbers of all subarrays, which is the hard problem from this week's LeetCode Contest. And so in this problem, you're given an array and you are asked to get the imbalanced numbers of all its subarrays, and by subarrays I mean contiguous subarrays. So let me just explain what they mean by that. So let's say we have this like 2, 3, 1, 4. Let's take every single subarray here. And it's saying for the imbalanced number, it's going to be in the sorted version. So let's see what that's going to look like. So we have an array of 2. So by the way, I'm not gonna draw one link subarrays because in a one link subarray you don't have an imbalanced number, so we're going to skip those. Like an imbalanced number for a one link subarray is going to be 0. So we're going to have 2, 3, 1, 2, 3, 1, 4. We have 3, 1. A little bigger. 3, 1, 4. And finally 1, 4. And so we need to count the imbalanced number in the sorted version. So in the sorted version, this is going to be 2, 3. This is going to be 1, 2, 3. One, 2, 3, 4. 1, 3. 1, 3, 4. And finally 1, 4. Okay, so the imbalance number, but what they mean is for every gap, like for every two numbers, if there's a gap of more than one, then there's an imbalance. So here there is no gap, here there is no gap, no gap. There has to be a gap of more than one. Here there's no gap. Here there is a gap of more than one, there's a gap of 2, so now we have 1 imbalance. Here there's a gap of 2, so we have 1 imbalance. And then here there's a gap, so we have 1 imbalance. And if the gap is more than 1, then it's just 1 imbalance. So like just because this gap is more than 1, it does, you still count it as 1. So here we have 3 total imbalances. And as you can see, it's 3 total imbalances. For this 1, 3, 3, 5, I'm not going to draw out the whole thing, but you can see like they show the imbalances in all the subarrays that exist. So you can see in this 1, 3, there is an imbalance of 1. In this 1, 3, 3, imbalance of 1. 1, 3, 3, 3, imbalance of 1. Here there's 2 because there's 1 here and 1 here. Here there's 1 right there, 1 right there, and 1 right there. Okay, and so the imbalance numbers in all subarrays is 0. So the imbalance number is the imbalance of all the numbers in subarrays. Okay, and so how do we do this problem, right? So let's think about it. For this, just this 2, 3, 1, 4. So pretty much, what would be like the brute force of doing that? Well, that would be pretty straightforward. So we would have a loop for all left ends of the subarray, all right ends of the subarray, right? So we'll just like loop through every single possible. This will give us every subarray. We can sort it, and then we just go through, left to right and just count up the imbalances. What's going to be the time complexity of that? So this is n, and this is n log n. And so that's going to be n cubed log n. Okay, and let's look at our constraints. So typically for these hard problems, you always want to look at constraints because it'll kind of tell you like what's the worst case algorithm I can use. So here this is 1,000 elements, and so for 1,000 elements, something like n squared will pass, but n cubed is going to be 10 to the 9th, so that's not going to pass. Something around, I think LeetCode crashes on like 10 to the 7th or so. Don't have to take my word for it, but it's around there. 10 to the 6th, 10 to the 7th, anything more than that, not going to work. Okay, so let's figure out how we can get rid of one of these. And so what we can actually notice is, like, let's take all subarrays that start with 2. Once again, we're not going to count any subarray with 1 element, but it's going to be this, this, and this. And notice that we can actually go from here to here in one loop. We don't actually have to sort these. Like if we get the imbalance here, let's say we get some number, right? Then to get from here to here, we just have to figure out what's the imbalance of when we add the 1 from the old one. And then what's the imbalance when we add the 4, right? And so in this case, how do we calculate imbalance? So let's actually start with the 2. So what we need to do, because we can't really sort these, because sorting is going to be expensive, but all we need to do is check for imbalances. When we put in a number, we just have to check are there elements to the right of it, and are there elements to the left of it? And they also be one, like, there only has to be an element one greater or one less. So let me show you what that looks like. So we're going to have actually a set for these numbers that we're going to be storing instead of like an array or sorted array, because then we can just check, is like n-1 in there, and is n plus 1 in there, and we can check that quickly. And so let's take a look at this. So when we first have this 2, obviously we're not going to have a total because that's one element. Now let's add a 3. So when we add the 3, and we're going to keep adding these numbers into the set. So we add a 3, and what we can do is we can actually check, is there an element to the left and is there an element to the right? And so when we add a 3, so the element to the left would be a 2, and the element to the right would be a 4. And so there's a couple of possibilities that's going to happen, and I can tell you, and I'm going to go over what our count of imbalances needs to be. So if there's one element to the left or to the right, if there's only one element, we're going to add the number, and then we had one, like, we're just going to make this connection that does nothing. So we're not breaking anything, but we aren't helping anything either. And so that can happen in and if you think it doesn't work in the middle, well, let's take a look, right? So if we have like a 2 and a 5, and we add a 3, this connection is not an imbalance, and so we're still fine, right? So if there's one element to the left or to the right that's like 1 or less, then our net sum is 0. So one element, let's just say either direction, our net sum is 0. Okay, now what's another possibility? So let's take a look. So another possibility is, let's say there are no elements to the left or to the right, and remember, our set has to be greater than 1, because for a one element, we can't have any, there's no connections or anything, so that's always going to be 0. So let's see what happens there, right, where there's nothing anywhere. So let's say we have a 2, now we add a 4, and now there is no element to the left or to the right that's 1 or less than or equal to, right? So here, if there's 0 elements, we're actually going to add an imbalance. And we can try to do that in the middle as well. Like, let's say we had a 2 and a 6. There was one imbalance, right, between the 2 and the 6. Now we added a 4, now there's 2 imbalances. There's one here and one here. So if there's 0 elements, then there is one imbalance. Plus 1, sorry. Now let's see what happens if there are 2 elements. So there's an element to the right and to the left that are one greater and one less. So let's say we had a 3 and a 5. Now we had a 4. Now when we check, is there an element one greater and one less? So there is one here and one here. And now we had an imbalance, but we actually broke it. And so that's how you know that you broke it. Whenever you add something, if there's an element to the left and to the right, that's like, the number +1 and the number -1 both exist in our set, that means we broke our imbalance. And so that's our last case. So if there are 2 elements, we have a -1. And so really what we can boil this down to is, if there's one element, it's 0, but we don't really care about that. We care more about maintaining a balance. So let's get rid of this. And these are 2 cases now. Oh, there's one more case, by the way, actually. So if there was a 2 and a 3, if we add a 3 again, regardless of where, you're never going to create or break an imbalance adding a number that already exists. Like if we had a 2, 3, let's say we had a 5 here, where there was one imbalance. If you add a 3 again, it's like the same thing, right? So if you add duplicates, it's not going to do anything. So if there's these 2 cases, there's going to be something if the set is only one element. So if there's set length equals 1, let's just call it set length equals 1, then there's no change. And if, n is in set already, then there's no change as well. So this is going to be set length equals 1, we have 0, and then if n was in set already, it's also 0. Okay? So now let's keep going through this, and let's actually walk through how we would get a total. So what we're going to do is, for every single new left index, we are actually going to make a new set, because we're like going through the array and getting subarrays now, and we're going to make our total 0, but then we're also going to have a global variable. So let's just call our global variable like g, and let's call our current total t maybe. Okay, so for this 2, this is a subarray of length 1, so remember, subarray length 1, we don't care. Now we're going to add a 3, so let's add a 3. Now for a 3, we're going to check to the left and to the right, and there is one element to the left and no elements to the right. That means we don't care, right? That means the net change is going to be 0, so we can move on. Now we need to add a 1, And so you can see we're getting all the subarrays that start with 2, you know, in one pass, which is really good. Oh, and by the way, also, so as soon as we're done with the subarray, whatever our total is, we need to add it to the global every time. So like when we're done with this subarray, we need to take our total and add to the global. Whenever we're done here, add our total to the global again. So far it's 0 though, so it's not going to do anything. But let's keep going. So now we add a 1 to the set. So we're going to add a 1. We're going to check for the 1. And I'm just showing these sorted subarrays on the right. We're not actually going to have sorted subarrays. It's more just for visualization. So we're going to add a 1. So we have a 1, 2, 3 would be the sorted array. Now we're going to check to the right of 1. Is there something? Yes. We're going to check to the left. Is there something? No. And so remember, we either care about 2 or 0. This is 1. So we don't care. So we would push our total again. Then we keep going. Now we add a 4. So a sorted order array would look like this. And then is there something to the left? Yes. Is there something to the right? No. So then we don't care. We keep going. And so now we went through every subarray that went with 2, and we found that there were no imbalances. So now we actually move on to subarrays that start with, we went through every subarray that starts with 2. There's no imbalances. So we were here. Now we have a new left, so we're going to actually update our set. So this set gets deleted, and we're going to have a new set. Let's actually just delete it. And we're going to reset our total, but our total was 0 already. Okay, so we have the new set. Well, let's find out. Okay, so now we have this subarray 3. Remember, subarray length 1, we don't care. It's never going to add to imbalance. Now we do this subarray where we add the 1. So we're going to have 1, 3. We need to check to the left. There's nothing. Check to the right. There's nothing. And so if both of them are nothing, then that's this condition here, right? Where there's no elements. There's not n plus 1 or n minus 1. And so we need to add 1 to our total. So now our total is going to be 1. And then at the end, we need to push that to the global because we're done with that set. So now our global is going to change to a 1. And by the way, so we did add element 1 and element 3. Sorry, we added element 3 first, right? Element 3 and element 1. Okay, now we are adding the 4. So here this is 1, here this is 0. Now we are adding the 4. And as you can see from the 4, you can just use the old total and figure out how adding the 4 changes it. So we're reusing old totals and then modifying them, and then just we push them into the global at every single iteration. That way we have an n squared complexity instead of n cubed. So once you realize that you can make these subarrays starting with something in a one pass, like every subarray starting with 2, we can get in a linear time, then we can have an n squared solution. Okay, so this 1, 3, 4 now, right? So we added the 4. So is there something to the left? Yes. Is there something to the right? No. So then we don't care, right? It's one element. So that means we're going to have a net of 0. So we're going to have 0, but it's 0. It's the old result plus the 0, right? So it's 1 plus 0, so this is still 1. Okay, and now we're going to push the total to the global again because this is a brand new subarray. So this is a 2. Okay, now we're going to get rid of this. Now we're going to go to every subarray starting with a 1. And the only one is 1, 4, so we're going to delete our set here. So we have a new set, we have a new total of 0. New set is nothing. So we're going to push the 1. Can't do anything with the 1, you need 2 elements. Now we're going to push the 4. Now we check to the left and to the right. Nothing, nothing. So then we are going to add 1 to the total. So the total will be 1 because that's this case here, 0 elements. Okay, now we are going to push the total to the global because we're done with that subarray. So our global will be 3. So here our global was 0. Here our global is 1. And so that's everything for this one. And so what you could try to do if you still are a little hazy is maybe go through this with this. And you'll see that, like, so we can do a little bit of it. Let me show you this part. And this is why adding the same number doesn't change it, but it still does. So let's actually go through every single subarray that starts with a 1 in this example. So we have this 1, 3, 3, 5, 3, 3, 3, 5. And we're just going to go through every subarray that starts with a 1, and then we're not going to do the rest because there's too many, but yeah. So we're going to have a set, we're going to have a global, we're going to have a total. Okay, so we are going to start with the 1, add it to the set. So our set's going to have this. Global is going to be 0, total is going to be 0. Let's make it bigger. Okay, so we're going to have the 1. With one element, we don't care, remember? Now, I think this was actually, yeah, there was no 0, right? Yeah. So this is like the array here. There we go. Okay, so now we have the 1, 3. We add a 3. We check to the left. Check to the right. Nothing. That means we need to add 1. So we are going to add 1 to this total. So our total will be 1. Push it to the global. Global will be 1. Okay, now we add another 3. And so every time we add, remember, every time we add the same number, the total doesn't change. So it's just going to be the previous total. So this is 1, this is going to be 1, this is going to be 1. Yeah, so 1333 is going to be 1. So let's just say we push, so we can only have one set. So, but we do push to the global every time. So like this one gets pushed to the global, this one gets pushed to the global, and this one gets pushed to the global. So after these 3, the global will actually be 3. And now finally we add the 5. And so for the 5, and remember these sorted arrays, we're not going to have this just for visualization. The 5, is there something to the left? No. Is there something to the right? No. So then we're going to add to our previous total. So that's going to be a 2. Push it again. It's going to be 5 now. And so that the global will be 5 for every single subarray that starts with a 1. And we went through every single subarray that starts with a 1 and a 1 pass. So that's definitely going to be faster. Okay, so now I think we have everything we need to solve this problem. So let's do that. So let's actually code this up. So what do we need? Well, we need our global result. Then we need, I think that's it, right? And then we need to have a nested for loop. So for I in range length nums for j in range. And so this right bracket of the subarray needs to start at, the earliest it can start is the I. So for j in range I length nums. So we have our nested for loop. And now let's and we also need to make a set here. So we can just say cur equals set total equals 0. So this is going to be our current total in our set. Okay, now if nums j not in cur, then we need to add it. So cur.add nums j. So if it is in the result, we don't have to do anything here because we're not gonna, our imbalance number is not gonna change as we talked about. If we had the same number multiple times, we just need to push to the total at the end. So there will be like a push to the total at the end where it'll be res plus equals total down here, but let's do our code up here first. Okay, so cur's add, and then if length cur is greater than 1, yeah. So if the length of the cur is greater than 1, that means there might be an imbalance number. So now we need to have our 2 checks. And remember our 2 checks. So our 2 checks are if nums j minus 1 not in cur nums, or just cur, and nums j plus 1 not in cur. That means that when we added our number, there was neither a left and a right, or a right, so we're going to create a new imbalance, as I showed before, right? Like if we have a 3, and then we have a 7, and then we had a 5 in the middle, this is going to happen, and we're going to create a new imbalance, right? So for like this case, 3, 7, this had 1 imbalance, now we had a 5 in the middle. That would make it 2 imbalances. So we need to add to the total here. And then our other case when we need to subtract is the opposite of this. So if they're both in there, plus 1 in cur and nums j plus 1 in cur. And that would be the case of like we had a 3 and a 5 and we had a 4. So now they're both in there, the left and the right. Then we need to subtract. Okay, so now that we updated the total, this total needs to push to the result every time, because this is essentially every time we do this loop, we get a new subarray. So at the end of every single one of these, we have to, it shouldn't be in this statement, it should just be there. Okay, and now we finally return the total, or the result. So let's see how many errors we have. Perfect. All right, so this should be numsj plus 1, plus 1, plus 1, minus 1. Okay, let's see, that's one error. Hopefully we have more. Okay, so we have an error with the counter here, so let's figure out what that is. So let's see. For nums and length nums, if numsj not in cur, yeah, so that part makes sense. Cur.add. If the length of cur is greater than 1, that makes sense. Okay, so if numsj minus 1 is not in cur and numsj plus 1, we need to add 1. And then, oh, this needs to be a minus. Okay, nice. Okay, so you see we have an efficient solution, but there aren't too many solutions here, so I wouldn't really care about this too much. Like for new stuff, you can be wherever there's like 6 solutions or who knows. Okay, so let's figure out the time complexity. And like I said, I did talk about this earlier, just so we'd have a, a running solution. So we have a for loop that checks every single left boundary. We have a for loop that checks every single right boundary. And so that's going to be n squared solution. And for the space, we have a set. Worst case scenario, the set will take every single number if they're all unique, which will be of n, right? Like, let's say the left is the first index, the right is the last index, and all of these numbers are unique. Then you would take every single number into the set. Okay, so that's going to be all for this problem. So if you did like it, please like the video and subscribe to the channel. And we did get over 200 subs today, so thank you guys for that. And I will see you in the next one. Thanks for watching.